previous lesson, we talked about how power is generated and where it's generated, and this time we're going to talk about how we move that electricity from where it's generated to where we want to use it in our homes and businesses. So there's two main systems that are used after the power is generated, and that's the transmission system, and then right before it comes into our homes and businesses, we've got the distribution system. So our transmission system, as our video is going to go through, is our power is generally, don't quote me too much, 10,000, 12,000 volts at the power station. It'll go through a substation, it'll get stepped up in voltage, so that means we'll have less losses as we move it, up to 300,000 volts, 500,000 volts, and then we have this very high voltage and it gets transferred right to where we want it, and then it will get stepped down at those little green boxes in our suburbs. It will get stepped down again till it's about 11,000 volts, and then it will, from there, it'll come into our streets, and then that's where it drops down to our 415 and our 240 volts. And that's our distribution network. So what we actually want to use in our homes. And here's a little video on the difference between them, and maybe a little analogy that might be a bit easier to follow.
Welcome to an inside look at how electricity travels across the Southwest interconnected system to power our lives. Western Power's role is to deliver a 24/7 essential service to Western Australians. Safe, reliable, and increasingly renewable electricity supply for our 2.3 million customers. We build, maintain, and operate the electricity network that brings power from the generators to the people and industries. The network has two parts: transmission and distribution. Imagine our electricity network as roads and highways. Transmission is the highway. It carries high voltage electricity in bulk across long distances from generation sources to large-scale customers with huge usage needs, and to our terminals and substations, our on and off ramps. Exiting the highway, we come to the local roads, the distribution network. Here, electricity is transformed to lower voltages, suitable for use in our homes and businesses. The transmission network consists of large structures, and long lines are essential for moving vast amounts of energy efficiently. These feed into substations and terminals that push the power out, forming a web of interconnected lines in both the transmission network and the distribution network. The size difference is stark.
So obviously we can see, my students probably find this very annoying. I usually pause videos about 30 times to explain things, but I've tried to keep it to a minimum today. These are some power lines that you guys will probably not see around us in the suburbs necessarily, but if you go on any sort of drive, you'll start seeing these bigger power lines. That's the transmission system, that's our really high voltages. And these tiny little ones, if you can even see in this classroom, these are more our distribution network. So they're quite physically different. That's for safety, like we mentioned. And yeah, what's involved with the transmission system is obviously a lot more to it, so that's why they're so much physically bigger.
Large transmission equipment for the heavy lifting, and smaller distribution gear for the final leg of the journey. When the network was created, there were only a few power generators, so the transmission network was relatively simple.
Yeah, so we know there's power stations in these locations, and that's mainly what our grid used to consist of. It's getting it from these power stations, which are in those less desirable, cheaper areas, slash where we're actually getting the materials. So inland is probably where our coal is produced, etc. And the coast is where we can ship things into easily. And that was all the considerations, and then we just had to bring it back to where people live, and that was it. And as we're introducing the renewables, our grid's getting more and more complicated. We're required to store a lot of this energy that's produced by renewables, and yeah, it's just getting a lot more complicated at the moment.
We're preparing the network to integrate more large-scale renewables and the retirement of traditional power generation methods like coal, supporting communities and businesses in meeting our shared decarbonisation goals. Therefore, the network is becoming larger and more complex, and the transmission network is evolving, extending to connect these new sources to the grid. This growth is vital for our cleaner energy future. It ensures that as energy generation becomes more diverse and spread out, safe, reliable and cleaner remain top priorities. We're embarking on an unprecedented era of transmission expansion as we design, grow and maintain a network for life.
So that was the first thing I wanted to go through. When we're talking about transferring electricity in Australia, where we mainly use AC, like I wrote up on the board before. AC typically has less losses than DC. I don't know if anyone's ever done anything in their cars with extra batteries or any accessories in their cars. No one's ever played around with that. They've just got other people to do it, or no? All good. What you'll find with DC is if you install something in the car without quite a large cable, you'll lose a lot of that voltage very quickly. The resistance, it just adds up to a point where the 12 volts you're putting in from your battery, by the time it gets to the end of your car, you might only have 7 volts. Then that little water pump you wanted for your shower doesn't work. So what we typically do to prevent this happening is we convert things to AC to move them around. I could do a whole lesson on why we chose that. Recently it was brought to my attention by a student in the class that we do actually use DC to transfer electricity really long distances. It's super expensive. The infrastructure is really expensive to maintain, but the losses can be lower once all of these things are put in place. And it's something I learned in the class from a student, which was cool. After telling everyone that we only do it in AC, so that was a little. And then I sort of thought about it, and we don't typically do it in Australia. The only place that I could find that we do it is between Tasmania and the mainland. So for undersea cables, which obviously being Australia we don't typically have a lot to do with, but throughout Europe it's used quite a bit between countries. They convert it over to DC and transmit it at these huge voltages, but typically transmission is done in AC because of the cost and the way everything is set up. So I did mention it before, but does anyone know the voltages we typically want in our homes and businesses? 240, and what's the other one? That 415 is generally the other one. That's three phase power for anyone that doesn't know. So they're the typical voltages we want in our homes and businesses. They're just the most useful for us and easy to use. That's where everything works out. Sort of cover that, but did anyone else have any ideas as to why we transport electricity at such high voltages? Yeah, basically there's resistance in the cables, and what you put in at one end isn't necessarily going to make it to the other end, starts in the cables that are not slowing down, just restricting the flow of the electrons. So that can be mitigated by having bigger cables. The bigger the cable, the less resistance. But then what's going to happen if we make all our cables this big?
Heavy.
They would become very heavy, and more materials, more cost, bigger poles, more support. It just doesn't work. So there has to be
just run them underground.
can definitely. Heat's another thing that we want to try and avoid. More heat, more resistance. So when you do run things underground, it's like a bit of a blanket, and it can keep things cooler. But yeah, there's a certain point where having the cables be bigger and heavier, the benefits are outweighed by the extreme cost of cables. So it doesn't typically, there's a point where that would stop being effective. Does anyone know the main metals we use in cables?
Copper and aluminium.
Copper and aluminium are two most common current carrying metals. Copper ever so slightly better. If you were to get two identical cables, you'll get a bit more out of the copper than as far as carrying current. And yeah, just those are some of the things. I've just ruined my next talking point about if power lines can have less losses when they're bigger, why don't we just use huge cables? But obviously the cost is the next thing which you guys came up
You
with.
have to have the poles a lot closer.
Yep.
Because
Yep.
you need more poles, which is
More
quite
poles, bigger poles, heavy cables. It all just, there's a point where the losses are acceptable versus, yeah, it just doesn't quite work forever. Like you said, having them underground can make them less dependent on weather. So yeah, heat can affect power loss, more heat, more loss. What's another benefit?
Did the power lines heat up? Is that what?
Because we're sending a current down it, and that current, if you can think of electricity as moving electrons, you don't want them to be hitting anything on the way, but they do, and that's what causes the heat. So when the electrons are bouncing off,
Yeah, okay. Yeah.
it's not how it actually works, but to visualize it, that's what's happening. They're bouncing off things, and if something has a low resistance, there's less stopping it. And so there'll be less heat and less loss. Sometimes it's quite desirable if we're trying to heat something up. We want it to have as many restrictions as possible. That's when you see your light globes and like a heating element, when they get really hot, it's a high resistance material, and that's what's happening there. There's a lot of collisions for the electrons to hit, and that's where the heat's coming from. Can anyone think of another advantage to having something underground aside from it being protected by the weather a little bit? Nobody wants to look at power lines.
Oh, yeah.
Correct. They're a little bit ugly.
Safer for wildlife, birds.
Definitely. You've seen a bird fly into two parts of a power line. It's spectacular. But in both of those things, what we can think of as well is maintenance. It's not going to get damaged as much if it's underground, right? Correct. Yep.
Dudes on helicopters.
It's cool. It's cool. Cranes are one thing, but yeah, that's another. Cool. So, what we have on the board here is what would typically happen. I was trying to find an image that really suited the voltages we use in Western Australia. We don't quite go as high as 800,000 volts, but yeah, that's sort of, if you can imagine before this, and I think one of my other images has it, where over here we're generating our power at our power stations. It's like I was saying, comes out of the power station at 10,000, 12,000 volts. And what happens is it goes through a substation, which is like we call them transformers. One voltage goes in, another voltage comes out, basically. It's as far as we have time for today, but we basically want the voltage to be as high as possible so that the losses are as low as possible. So we start at 12,000 and we'll go through a substation doing the reverse of this. Instead of bringing it down, we step it up to these voltages, so 800,000 or 400,000. Got what we use in Western Australia typically, 330,000, 275, 132 and 66,000. So a little bit different to this, but very, very high still. It will go those long distances at the really high voltages, and as we come into our cities and suburbs, we're going to step it down to these lower voltages. These are the little boxes I was talking about. I know I've got one in my closest park. There's a little green box, and that's where it'll step down from 33,000 to 11,000 volts for the suburb. And then from there, it's going to come along to each home and business and either give it 240, or if you've sprung the extra money, 415. I don't know if anyone has any 415 at home for any big sheds. No? Unless when you don't want it to happen. Cool. So yeah, these are our typical voltages we'll want. Some houses do have 415 to them for big bits of machinery, big lathes or whatever people have in their back sheds, but it's not typical. Another little point I've got is regular inspections and maintenance can help prevent losses. So knowing that something's like you do your crane inspection every morning, if they do periodic inspections of the lines, they can pick up damage before it becomes an issue, or a power line falls, or a pole rots through, or a bolt's all rusted and a line comes down. So lots of that can help prevent losses. I do have another little quiz here that we can work through. There's no quiz in my third session though, so that's good. So let's just work our way through that. If there's one that we haven't quite covered, we can talk about it. The second one, voltage. Volts is just the V, the K is 1,000 volts, and the capital M is 1,000,000 volts, which we definitely don't go near in Australia. These images are basically the same. We have a power plant, a step-up transformer, our high voltage transmission lines. We step it down at a substation. We have our 11 or 13,000 volts into the suburb, and then that shoots out 240 into each house, or 415 if that's what we want. So we have our high voltage electricity from where it's generated right to where the substations are in our suburbs. So that's what the transmission system does. It just moves it from where it's created to close to where we want to use it. Jim, did you get number 2?
I've got 111 kilovolts, 500 kilovolts.
Yeah. Yep. So I was saying that anything 11 and under, and even lower than that, would be part of our distribution system. But 11 to typically 500,000 in Australia would be high voltage transmission lines. I was looking a little bit at the American grid the other day. They go right up to 880,000 volts. That is some weird stuff over there. Yeah.
Not Americans.
No. Everything's interconnected, but then like Texas isn't. It's just its own system, which is why they have huge problems when there's snow and hot weather and stuff, because they're not actually connected with anyone else. So yeah. The main reason for using high voltage transmission lines, Tracy?
Actually missed that question.
Missed it?
No.
That's okay. We didn't go into it heaps because I didn't think we'd have time to do it, but we want to reduce the current by putting the voltage up to minimise any energy losses.
So what number was that?
3.
Number 3.
Oh, 2.
Yeah, look, some of the wording is a little like I'd love to have more time to go over some of these, but that would be the one that I would do. Not a major component of transmission systems.
3.
The fuse in our household circuits, so it stops being the, say, Western Power's problem once it gets to your house. That's now part of your system. So that they're in charge of the transmission distribution, and then once it comes into our houses, so the protective fuse, or these days circuit breakers, as we'll wire up in our next session would be. That's what we use now. Distribution systems responsible for, Sean, if you've got number 5.
2, sorry.
Yep. Yeah, cool. So we generate it, we transmit it, from there we distribute it into our homes. That's the distribution system's job. Did anyone manage number 6?
Was it 2?
Yeah.
I thought it was 240 though.
Look,
Used to be.
it used to
Oh,
be.
okay.
We still say 240, and in lots of places it is. Lots of our calculations are now 230 and 400 volts, even though we say 240 and
450.
415.
But yeah, I did get it.
Yeah, and if, I don't know if anyone's ever measured the voltage that comes out of a PowerPoint, I hope Tracy has it at some point, you're going to get anywhere from high 220s up to 250 plus, 255, and for most equipment that's fine. Some have really small windows, they might only work from 235 to 245 volts, so you might start encountering issues when you've got little fluctuations in power. Anyone manage number 7?
2.
Yep. Cool. Number 8.
2.
I know I know it's what
This one,
Make everything
no idea.
two.
I just guessed this one.
which of these statements about energy loss and transfer? Yeah, look, we didn't quite get time to go into Ohm's law, but that's fine. Which of the following is a modern feature of distribution systems aiding efficiency and monitoring? I got smart meters as well for that one. It's obviously didn't used to exist. It's just something that, because we're getting energy from so many different sources and we're home at different points in the day, we're using this system to just monitor things. It can also help with reading the meter. Somebody would have used to have to go and look in everybody's meter box, and now the use of stuff like this allows them to just remotely view it.
When there's a blackout, you
Yeah,
can see that there's a blackout.
yeah.
Stop maybe
Yeah,
putting
fine.
magnets on there to slow the spinning in down.
That's not a bad one. Just get your neighbour's power. Bypass the meter completely. We would never do that. And number 10, which combination correctly matches components to their respective systems? This one was a little bit.
Two?
Yeah. Yeah. That's the one that makes sense to me. Alright. That was our last painful little quiz we have to do, so that's good. And if we didn't get it, that's fine. I think between us we got the answers. So now we're sort of probably thinking about power a little bit more than we have in the past. Maybe not for Tracy, but we just accept that it's there and we use it for the things we want to use it for. How would you cope if the power was out in your area? What infrastructure might be affected? So let's just think about power that we would use, say, getting home or once we're home, or a couple of those things. What's
Probably the biggest thing will be traffic.
Yep, for travelling, absolutely. I'm sure we've all been through a set of lights where the lights are out, right? Imagine if that was happening across the city. Wouldn't be
Trains
ideal.
not running.
Yep, absolutely. Yeah, with that, I'm sure we've all, like I said, approached those traffic lights. Like, it's sort of a little bit.
You can pay for your shopping.
Yes, who carries cash? Enough cash to do their weekly shop these days.
Hospitals, which are struggle. I suppose they've got backup plans.
They should.
Generators.
They should. Have we turned everything off and tested that everything runs off that generator lately? What else every day that's going to affect us? Like we said before, our lighting and our heating.
TV.
It's not so bad in summer where it's light till almost we go to bed and from when we wake up, but in winter, you may want lights before the sun comes up at 7:30 or.
Well, it's long-term power cut these days. You're not going to charge your car on.
No, I'm not going for it.
Yeah, can you use a petrol station without any power as well?
Well, you can't charge your electric car up at home to get to work the next day.
Yep. Yeah, tons of things. Super dependent on it. Yeah, so it really does affect us in lots of different ways. We've been through our test. We should now hopefully be able to identify whether a component or a certain voltage is part of the transmission or the distribution system. May not be a distinction we might have made in the past. It's just they're all power lines. They'll get the power where it's going, but hopefully we know that we use 415, 240, and on the transmission side in Western Australia we've got 330,000, 275, 132, and 66,000 volts. We talked very briefly about why we use AC over DC. And that we use DC for undersea cabling. And we're just going